Yeah, well, welcome to today's webinar. My name is Eric Schmiglo. I am a director at the data consultancy Hivemind Technologies, and I'm joined today by Jaime.
Hello, thanks, Eric. A pleasure being here with you today to talk about something near and dear to my heart, which is energy. So my name is Jaime Lopez. I'm the head of marketing at Ververica, and I have a background in energy engineering, which makes this especially interesting for me today.
Cool. So today we're going to talk about exactly that. So about specifically data infrastructure in the context of energy. Maybe we can move to the next slide. So really about how we can use the streaming data lakehouse concept to build modern data architectures for real-time requirements in businesses. This powered obviously by Apache Flink. This is a joint presentation by Ververica and Hivemind. So what we're looking at, what's the vision really? Currently, businesses have to operate on data intelligence. So really what we need nowadays, especially in terms of like high volume, high velocity businesses, is the ability to take real-time decisions in real time, right? Getting the data as quickly as possible. And based on that, taking either business decisions or even automated reactive decisions and use those data inflowing data streams to be able to predict what the future could bring in different scenarios. That also requires the ability to be analytical and have dashboard insights and use ML models, but also being able to unify streaming data input coming from sensors, IoT, etc., with batch processes, and all of that built on a unified data model. Right, so really about being able to merge real-time decision-making and long-term view, long-tail data storage. What we want specifically is a single source of truth in a platform that serves every workload, every business use case, from operational requirements to analytical decision-making and intelligence, all of that in real time. So essentially, when we're looking at what most organizations struggle with, and that's really just siloed data systems that operate and exchange data in batch processes, and why this holds us back, right? It's slow, it's basically relies on our orchestration, on schedules. We even have currently one of our clients, they have to really wait until 36 hours until they really can safely say that everything has been processed properly. And that's really crazy because you basically take decisions a day or a day and a half after they happen. This is what really holds businesses back. So essentially, when we're looking at the hidden cost, right, it's not necessarily always obvious because people just say, well, you know, I'm working with department A and they're going to deliver their results in regular schedules, it's fine, and we can work with that. And we've been working like that for years now. The problem is that there's creeping issues with it and things that are not necessarily completely obvious. So there's operational fragility, right? When long-term batch processes break and fail, well, you have to wait until the next batch cycle until you get the data, right? And that also implies retries and failures. You have scheduling dependencies. Maybe you need to backfill. So a lot of that operations need close monitoring and orchestration. Obviously, we've also seen that can lead to delayed decision-making, like the 36 hours that one of our clients have to wait until they're really, really sure that they have all the insight that they need. And then there's the issue of governance, right? You don't necessarily know when and where the data comes from and when it is going to arrive. There is no lineage, it is incomplete, and there is often the problem of limited audits, right? It's really difficult to tell, did I see that data before? Has it been merged recently, or is it a new delivery, et cetera, et cetera, et cetera. And as businesses grow, the batch chains also grow. Right, indefinitely, you have long chains of interdependent processes and at some point infrastructure fails, and you can't throw indefinite amounts of hardware at the problem.
All right, I just unmuted myself. I'll take over now for a few slides to continue building up on the point that Eric just made. That batch architecture can hold you back and will hold you back and will prevent you from realizing the value that your company could theoretically realize. And that is what Ververica is here for. And that's the question that I get very often is, okay, who is Ververica? We like to say that we are the architects of now. We are the providers of a real-time unified streaming data platform. Originally, what now is Apache Flink was created by us and donated then to the community, to the Apache Foundation. And based on that, we have created that unified streaming data platform. When you need to be right, but also make or take action right now, the marrying of that right and right now is where we come in. When with our product, you're going to be able to react in milliseconds rather than 36 hours, as Eric mentioned. We partner with leading players in the industry, from Booking.com to ING to Banco de Crédito del Perú, to help them realize value in real time. As I just mentioned, our expertise in this is unrivaled because we are the original creators of Apache Flink, and we power these real-time use cases in many industries around the globe, a lot of financial services, defense, technology, automotive. But we are here today to talk about energy, which is a very special vertical, and one where we have a few interesting customers such as Uniper, who actually leverage this ability to make decisions in real time. These customers are global, and because their needs are global, our offering is also global. It is available on-prem, but also on the 3 main hyperscalers and multiple regions around the globe. And provides that end-to-end solution in the, after all, to grab data from wherever it is, no matter how complex, outdated, or cutting edge the system is, to activate it, produce action, produce kind of intelligent business decisions in milliseconds, and then power those use cases that we just talked about. So whether that's an on-prem or a cloud or something in between decision deployment, we're going to be able to supply your needs or cover your needs so that your business can benefit from this. And about use cases, when it comes to renewable energy, which is the main topic for today, and what Hivemind has a high amount of expertise on, there are 6 specific things that Eric and I brainstormed before this webinar, where we believe that real time can make the biggest difference. Starting with the first one, which is real-time wind turbine health. When you are operating a wind farm or multiple wind turbines, you get continuous SCADA data on polling cycles of 10, 20 seconds. And that represents many different dimensions and physical phenomena, either temperature of components, vibration, rotor speed, and this will be typically the first place where anomalies are detected. Sometimes these anomalies are big enough that you might need to take action immediately. You definitely cannot wait 36 hours, otherwise you're going to have no turbine or a massive fire on a turbine. But you probably want to either disengage the transmission or decouple or depower the turbine before the next polling cycle of the SCADA to prevent a catastrophic failure. If you want to have a productive, profitable asset, first you need to have an asset and you need to have a functioning asset. So with this ability to react in real time, you're going to be able to prevent catastrophic failures, extend the turbine life, and keep your asset alive. The second use case, where Eric and I thought that we can make a really big impact, and we have some examples live already, is dynamic optimization of these renewable assets. If you can integrate real-time weather forecasts, real-time measurements with turbine controls, either the yaw of the blades, the pitch, the power curve, you're going to be able to react and kind of squeeze every single kilowatt hour available of that wind resource so that you can adjust your operations in real time and, as I said, maximize the energy that you capture, minimize the stress that you put on the blades and the rotors, for example, when you're dealing with crosswinds or those type of situations. So you can optimize turbine by turbine a whole fleet across, yeah, one park or multiple parks operating as a virtual power plant. The third use case is more on the commercial side, which is bidding optimization. Years ago, markets were only day ahead, and then they were like day ahead plus hourly. Now most of Europe is moving to 15-minute intervals. So there is a significant upside to be gained by being able to feed that real-time data to your bidding algorithms and react to the bid, adjust correct bids in the power market, but also capacity market, regulation up, regulation down, etc., in minute or 15-minute intervals. So you can align your output with price peaks and with demand fluctuation. So not only are you going to capture more megawatt hours of the resource, like in the previous use case, but you can also increase the value you capture from the market per megawatt hour you produce. In the end, the capex of your resource is going to be fixed, but the market value you can extract from it can be optimized through this sort of use cases. Moving on to something even a bit more advanced, which is smart maintenance scheduling. So when you combine that 10-second granularity level SCADA operational data with wind forecast data, long-term and short-term, with market forecast data, you can identify low production intervals. And in variable renewable sources, it is extremely important to set your maintenance schedules to take place on the low production intervals. Dispatchable power plants have the luxury to, have a yearly maintenance and stop for all August or whatever. And it's very easy to forecast, but wind turbines and hydro plants and solar plants don't have that. So with this sort of integration of data, you can schedule the maintenance when wind speeds and revenue risk are the lowest, and you can schedule your maintenance crews very efficiently, turbine by turbine, when the wind forecast tells you that you're going to have low output and it's not dangerous to operate. So you're going to reduce the lost output and you're going to maintain in a smarter and more profitable way. And now for something very, very juicy, which I think both Hivemind, Ververica, and particularly Eric and I are very excited, which is how to give renewable producers another lifeline and like a path to increase profitability. So traditionally, wind power has suffered from curtailment. That is when you are generating wind power, but the grid cannot take any more of it because of variability. There were some examples of this causing blackouts, like in Spain and Portugal in a few months ago. And that means that even when there is wind and the rotors are spinning, very often or often these are decoupled from the grid and you cannot feed that energy into the grid. Historically, for example, China has had curtailment of 30 to 40% of their kind of capacity, wind capacity, because their grid couldn't take it. But what do you do with that energy that could be produced? Well, have you considered battery storage systems? With this real-time data and grid balance data, you could trigger storage instead of curtailing the wind, and it allows you to, for the first time, build sensible business case for how much revenue could I gain from storage. So when you allow these batteries to absorb that excess power and release it when market data tells you that it's profitable or needed, then you can maximize the asset utilization of your wind turbines. You can have them producing basically every time that there's wind and support grid stability with your storage system. So you don't need to waste that wind. You can store it for later. And we have seen in practice that this is a fairly profitable strategy. And the last use case that I'm going to present today has to do with another additional revenue stream. So typically in Europe, if you are an energy producer that has both renewable and non-renewable sources in your energy mix, you operate in the ETS market, so emission rights. And for every megawatt hour of renewable power you produce, you're going to get emission certificates that you can use to offset your emissions from thermal generation or to stay under the cap that you are given by the regulator. If you only have renewables in your mix, what you're going to be generating are guarantees of origin. these guarantees of origin can be sold, which means that if you, well, can and are sold and are kind of the path to profitability for many producers. So for every additional megawatt hour that you can deliver because of this reactivity and responsiveness in real time, you are also bringing in a like double benefit, because you're increasing either the EUAs or the guarantees of origin that you're accruing and that can be sold to add to your bottom line. So you can strengthen your portfolio profitability, or if you're a captive producer, you can drive premium terms in PPA negotiations with your off-taker. And that's all from me. Now I'll pass it back to Eric for him to elaborate on, okay, how does this actually happen in practice?
Exactly. Thank you, Jaime. This is really, really good stuff. And particularly because I think that most operators of renewable power plants all constantly face the problem that there's a gap between what they could actually earn and produce with their assets and what they actually do, because like of physics and because of market regulations and because of the ability to offload their energy elsewhere. So this is a big driver. There are a lot of really interesting projects going up everywhere in Europe to utilize and to essentially take advantage of this ability to react in real time, to store excess energy in BSSS and sell it later, to really close that gap between what you can produce and sell and what you actually do sell, right? So cool. So let's take a look at what that looks like in practice, specifically from the grounds up, and how we can actually just collect the data from our source and pipe it through our system. We move to the next slide. Thank you. So generally, what we want to capture here is, in terms of the optimization of the energy production, we want to basically capture the real-time sensor data and the metadata to basically be able to visualize and monitor the assets in real time. And we want to combine that with weather data and forecast to be able to plan ahead how we're going to utilize our plant. For instance, when we're talking about predictive maintenance, being able to say, okay, we're going to have a low yield because of the weather. I'm going to schedule my maintenance in the next couple of days and do a rolling maintenance of my assets to make sure that I can still benefit from utilizing my assets as much as I can when there's wind, when there's the sun is shining, right? So that also gives us the ability to performance monitoring, and detect anomalies specifically before things really go wrong, and optimize the energy yield as it happens. What we also want to do is to continuously optimize our models, our predictive models that we generate on top of our specific of our plant metadata and the topology of our let's say our fields, and essentially thus create a bespoke yet optimized a data platform, a data analytics facility for our business. Essentially, what is really, really important is understanding that real time is absolutely key, because if we rely on batch, performance and money is left on the table. So what that looks like in practice is, and why the legacy stuff really fails us, is that if we're basically using stale or delayed data, we don't get the right predictions. We don't detect anomalies, underperformance as it happens, but only after the fact. And adding new assets or adding new weather sources is a manual process and requires manual labor to onboard them. We get problems and data quality issues in our models, and there's absolutely no way to specifically optimize and control the data flow if we have to wait for batches to specifically to finalize. So essentially, having a batch-oriented system is the wrong approach here. Because delay is crucial, and having delay is leaving money on the table. So how we do that in a Flink-powered data platform. So generally, if we have a flow of data. It starts from the left and goes to the right. We look at our data sources. So we have IoT systems, right? And normally we basically have like a variety of different SCADA systems, and all of them, because most SCADA systems are classic monolithic structures, they rely on scheduled and periodic log output or even data dumps. And of course, that's sort of batch. But what we can do is tune them to do micro batching. And the way we optimize this is by saying, okay, whatever SCADA system we have an integration strategy for it. We use standardized components such as Kafka Connect, or log collection mechanism to collect the data at source and push it into bucket store. For instance, in our specific use case, we're using AWS. So we basically connect our SCADA systems by pushing the data out of the log storage or in individual micro batches into an S3 bucket, and then using SNS bucket notifications to basically pipe the data from S3 into Kafka. In the weather data, weather APIs is essentially just connecting to APIs, REST APIs, using, say, a similar mechanism to make sure that we have a continuous data delivery of changed weather data input to our assets. We essentially stream all of that into our Flink streaming pipeline, which basically continuously lands the sensor data into our data lake storage, and combines and enriches the data with the other data streams. One thing that is very important also to note is that obviously in reality, we do not have one source with one schema, but we often have different schemas. And one thing that you usually do as a first step in our streaming pipeline is data normalization. So depending on the SCADA system that you have in your specific field and the partner that you're working with, if you're working with multiple fields, you'll have different formats. So the first step is to make sure that we have a common data model, which is essentially denormalization and let's say data projection of different models into one single unified model that we land. We're specifically using Iceberg here because we want to not only benefit from streaming and stream processing in Kafka, but we want to be able to continuously snapshot our data into Iceberg and use the Iceberg's formats, the Iceberg format's ability to do continuous upserts on our table formats. So we can basically combine continuous lookups of already landed data with incoming streams. Now, once that's landed, we have a separate process that continuously trains the model and delivers the model to our model serving layer, which is then called by our Flink jobs to enrich and predict the next data points within our streaming pipeline. So what this gives us is, as you will invariably see, there are some batch processes as well, because everything that needs condensation and compaction is more batch oriented. But the underlying paradigm that we have is a continuous data flow from our data source to our data platform, which gives us the ability to continuously stream our data into our platform and gain real-time insights at any time, at any given time. So when we're looking at common patterns across all use cases, is that we can see that depending on what you're looking at, you may have differences in sources, data sources, in outputs and requirements, but the underlying architecture is always pretty consistent. And we want to take a look at what that looks like in practice. So we have shared requirements. The first bit is real-time data processing. We want low latency and high reliability, a real-time stream and real-time aggregation of our inputting streams. We want to have access to live data as well as historical data, which is the reason why in the previous use case we were looking at landing stuff into Iceberg so we can do lookups and comparison as well as training. We want to be able to detect events and trigger processes when we detect anomalies, for instance, so that we can support automation of decision-making and alerting. We want to have immediate operational feedback loops so that we can specifically say, okay, if we do change this, this is the effect, and we can immediately action, decide and actionate things on top of these insights. And obviously, this also requires that we have standardized scalable storages, which is the reason why we chose Iceberg in this case. So it's an open standard that is well supported across the board, which means that especially in the energy industry, it becomes easier to share data with providers. So essentially, if you have collaboration with utilities that take your energy from your plant, they will also either feed back data to you for enrichment, or you will deliver data to them. Using a standardized format such as Iceberg greatly facilitates that collaboration. And lastly, end-to-end data consistency and quality enforcement is extremely important. You have full lineage control and data governance across the board, from your sensors at the very top of your stream all the way downstream to essentially the analytical and decision-making layer. These requirements require a modern data stack and a stream native approach specifically. So how does Flink meet those requirements? First of all, Flink is a streaming first framework, as opposed to other competitors where you basically started as with batch and you sort of try to do streaming by micro batching or other means. Flink was always streaming first, and essentially can support batch use cases as a specialization of the stream. If you want batch, it's just a standard that is a special use case of a stream with a long window, right? So specifically, also what you want is to have the ability to have exactly one's processing guarantees, so you're consistent. You're looking at, and you know that you're working on the same data set, and that you deliver consistent results. You want to be able to manage business logic specifically in your stream, and have the ability and support for real-time machine learning features, for instance, to integrate an ML processing layer or enrich one. And obviously, what's absolutely critical, especially for our energy use case, is low latency with high throughput and good scalability, right? And lastly, the support for a variety of formats, such as Iceberg, is extraordinarily crucial for an open and integrative data platform strategy. So in short, Flink is just not fast, it's precise, it's consistent, and does the trick. Right? So generally, when we look at a blueprint for a streaming data lakehouse, we basically have like two specific layers. One is the real-time streaming layer, which we've already visited in our energy use case with different, let's say, upstream data sources, be it databases, which is a standard use case where we integrate legacy databases using CDC. Flink CDC, for instance, is an excellent way to solve that problem, especially like in large organizations with big legacy databases, or in the IoT sector, like we visited earlier with our energy use case, where basically collects data systems from the source, or collect log and metrics from the IoT devices straight away. We all unify that into Flink streaming. We have real-time ingestion capabilities, and we can pipe that into databases for real-time apps, dashboards, etc. At the same time, Flink streaming gives us the ability to land everything in a data lake, for instance, Iceberg, where we can also then integrate batch processes, especially when we're looking at collaboration in the energy sector, when we basically integrate data deliveries from third parties that deliver, let's say, enriched data sets, reports, earnings, and whatnot in batch sources. And that gives us the ability with Flink to process these data sets and merge them into our lake structure for analytics and BI reporting. So this gives us a single architecture with one framework that solves pretty much all of our requirements in a modern data platform and data landscape, but specifically with real-time at the core and at the source, with scalability built in. So generally, we propose this as a standard blueprint for multiple use cases across industries, be it energy or manufacturing, which helps us like solve a lot of different business requirements across the board. So generally, when we're looking at how Ververica and Hivemind work together here, essentially it's a pretty clear division of labor. We have Ververica with the Ververica platform and the enterprise features as delivering the platform product, which is absolutely essential because in a lot of our use cases and conversations with our clients, they always ask us, okay, how do we actually manage operation? How do we run the platform? And how can we basically organize our Flink properties effectively? And most of them start with, let's say, the vanilla Apache Flink offerings, and notice how difficult that is and how much work it is to properly organize that. The Ververica platform solves these problems and offers better scalability and better operations. What we do in the mix is to help clients select the right architecture and also implement their use cases, migrate their existing workloads, and enable their teams to run and operate and optimize their Flink workloads and data platforms. So it's essentially the combination. The outcome is a reliable, functioning, well-supported streaming lakehouse that delivers security and speed to your business.
Just to add something to that, I think I speak for both of us when I say that most often what our customers want is a solution that works for them, and they're not looking to just hire a huge team to build it or anything, but they want the solution, not kind of the hassle that comes with it. That's why the collaboration between our two parties, I think, is very powerful, because it gives you the delivery, it gives you the peace of mind, it gives you the security without the hassle around it.
100%. We often say, it's best to solve your problem by composing it away as much as possible. So you can basically focus on really just implementing that one bit that is really unique to your problem, right? And using the Ververica platform and standardized components basically is part of that composition mix, right? Because it does away with all the operational overhead and the difficulties of training your teams to use the vanilla offerings, rather having a self-service platform that really helps and delivers the insights that you need to run Flink jobs and Flink applications effectively.
Couldn't agree more.
So generally, if we're looking at like a standard streaming project, how long that really takes, like the example that we just gave with the wind turbine platform is a project that took us 2 months from the inception to the go live in production. So essentially, it starts with the quick assessment of the success criteria, what the use cases are, and how we can what the MVP scope is. Then we write the blueprint, the run books, and a phase plan together with the Ververica platform. We pilot end-to-end to production and ingestion production slice that starts from ingestion all the way to the BI, for instance. And then at the end, we do the hardening, the runbook, and the handover. The idea of that, like MVP approach to streaming the lakehouse, we want to prove to the business, with our client, to everyone else in the business, that you can build successfully a streaming lakehouse within that short time frame if you focus on the things that really matter. Because the ugly truth of most streaming platform projects is that they take 6 months or longer to implement, because there's scope creep across the board. Focusing on the right tooling, composing your problem as much as possible until you basically just have the residual implementation overhead. That's the way to go, with fast feedback loops. So ramping up, as I said, is really just that quick start, environment bootstrap, a sample Flink application, all the way to iceberg. Then we have the blueprint sprint, where we basically build the target architecture, develop a cost model with the migration plan. And lastly, the pilot build, where we basically build the MVP and deliver an ops run book with finishing up with a health check and stability and data quality with SLA gap analysis. So essentially, really making sure that within that short time frame, we can build a streaming lakehouse project, an MVP of a streaming lakehouse end-to-end in production.
Yeah, and for us, it's extremely valuable to work with a partner like Hivemind because we know that what goes through their hands is going to be done operationally excellently. And eventually, when things go sideways, we're going to know and have an easy path to debug and to fix because things have been done in a composable, resilient, and structured way.
Precisely, thank you. So generally, it's operating and scaling. That's the lifetime. We basically operate with weekly ops reviews, monthly health checks, and optimize for cost and performance tuning, schema evolution, feature, with an enablement at the end, playbooks, templates. We also with pair programming and certification, this is how we basically cover and help our clients with Ververica for Flink projects. So I hope you enjoyed this webinar. It was really great having you today. And yeah, I'm happy to take questions.
Excellent, great. All right, let's see if we get any questions. Let me stop sharing this.
Mhm.
See. Yeah, here are some questions. Let's start with this. I think this is a good one for both of us, but let's start with you, Eric. Like looking ahead, how do you see AI and machine learning combining with Flink to further optimize renewable energy operations?
Yeah, I think it's a great platform for. I mean, first of all, we have to differentiate between generative AI and machine learning, right? So those are two different fields, right? So in the energy sector, the predominant use case is usually points to machine learning, essentially in terms of using sensor data values to predict upcoming behavior, right? So we essentially, and Flink is an excellent platform to do that. You land the data into your lakehouse, you can train your model, and then you can also serve your model within the Flink pipeline. So it's really great, very easy to do with a good support within the framework to basically integrate training processes as well as serving layer. We're looking at generative AI. That's a more interesting aspect. So first of all, we basically differentiate between two different patterns. The first one is the assistive pattern, right? Assistive pattern is essentially using generative AI to help business people within the company to ask questions and self-serve in BI reports and analytics. Like in the traditional way, usually when a CFO has a question or somebody from the business wants to know, hey, what was like last quarter's performance inside X, Y, and Z, they usually send an email, Slack message to a business analyst. The business analyst has to understand the requirements, formulate a query, create a report, and all that. It's a lot of work, extra ad hoc work. An assistive generative AI model can essentially understand the query of the business person and formulate and execute a SQL query against Flink SQL to basically generate that report without involving the business analyst. So the business analyst can actually continue doing the stuff that they do on frontline work, is essentially building, doing analytics and training models. And so that's the assistive process, actually very, very helpful. And there's a lot of room also for essentially for optimization within the organization when you have that kind of assistive model for generative AI. The other bit is what we call the observer pattern. So essentially it's a combination of, let's say, classic anomaly detection and a marking of, let's say, behavior with an agentic implementation of generative AI application that just says, okay, I'm getting, let's say, a fingerprint of behavior here, and it with the prompt of saying, is this an anomaly? Can you verify this for me, please? And using an agentic model with MCP, it can essentially, MCP tooling, it can essentially then compare the fingerprint with a database of failures and previous issues, and then create an alert and recommendation mechanism for operators what to do in case of an anomaly. This is actually a powerful model where you combine the power of streaming processes and deterministic aggregation and generative AI for better operations, right?
Yeah, I agree. I think there's like a bright future ahead for integrating both types of, let's say, deterministic / machine learning AI and generative
Yeah,
into this sort of architectures. The fingerprint recognition and like first line triage is something that we are seeing in a very different domain, which is security, InfoSec, SIEM. We
yeah,
have a few customers that basically utilize Flink as an anomaly detection engine to flag these things and like pre-process them or triage them, whether they need to be reviewed by a security expert or just kind of be noted flagged. Then when it comes to the first part of your answer to machine learning, I think that this is together with high frequency trading, energy operations and trading is probably the domain in which the payback for model performance is the fastest. A better
absolutely.
performing model literally means more euros in your bottom line. So being able to train and adjust your model faster than your competitor typically is going to give you an edge. And we are seeing cases where in a generative context, we can update in real time with Flink agent memory, agent
Yeah,
context, but also model weights.
yeah,
So if you bring that to a classical application, you can update model weights in real time. You're going to be able to outperform anybody who's not able to do that.
100%. And the interesting bit also in the energy context, which I think is like important to mention, it's like when you're an operator of renewable asset farm, in especially like let's say in Germany, there are a lot of operators wind farms that do not have BSS, right?
Yeah.
And BSS comes at cost. You can't just really just say, okay, I want to have like a BSS facility at site. I need to finance that. It's a financial operation. And it's often very difficult to finance that without being able to predict what the gap is, right? So essentially, using this platform allows you to predict how much output you could have generated and delivered to the grid
Mm-hmm.
at a certain time at certain market rates, and thus give the backing for a business plan that will allow you to finance and amortization of a BSS facility, which generally will benefit your bottom line. Right?
Yeah, and that opens the door even to project finance, where you can kind of finance it based, like purely based on the predicted cash flows of the BSS facility in the next 10 to 20 years, which means that an operator who maybe doesn't have huge financial muscle can finance it via project finance rather than having to go to like, I don't know, a non-recourse debt or like something more onerous, just
Yes.
because having this data allows you to forecast it and kind of explain it in financial terms, make it make sense in financial terms for a lender.
Yeah, absolutely. It gives really the little guy also that
Yeah.
same features and same access to
Hmm.
the kind of financial instruments that otherwise only the big players have, right?
Yeah.
Yeah.
Cool. I think we have time for one more question. I'm going
Mhm.
to pick between the ones that we have received.
Mhm.
Um, one that I think is very juicy. That will be a good closure.
Mhm.
And here it says, if you had to sum it up in one sentence, what's the biggest business advantage of switching to streaming data architectures for renewable?
Well, I think like from a business perspective, the biggest bit is that you stop leaving money on the table, right? That's like the most evident thing because it's not apparent, right? You think, okay, I've got a SCADA system. It tells me every day how much I produced and so on, right? You generally assume that that's fine, right? But switching to a streaming real-time decision-making platform will basically highlight specifically how much money you're not earning, right? By by actually, not being able to optimize or deliver the stuff at the right time or do predictive maintenance. That the one bit, especially with wind, is like specific. If you have a breakdown of your wind turbine, can be very, very expensive. You can extend the lifeline of your assets by doing predictive maintenance and also choosing when you maintain your wind turbines, especially when there's no wind, right? Rather than when it happens, right? So I think like it's really about, in terms of like the business value, and has less to do with technology. This is really just about money. So it's really making sure that you earn more of the money that you're leaving on the table otherwise.
I think that this is more a matter of when than if kind of
Yeah,
renewable energy moves to real-time data and streaming in general. Um, During the preparation for this webinar, we came across a quote that I have from a professor in my past that said that this is like trying to do surgery with oven mitts on.
yeah, I
That's
love
what
that.
happens when you try to operate a resource that fundamentally is real time. Renewables are real time, they don't operate in batches. So, batch systems were made in the time and for the power system was dispatchable, that you could switch on and off at will. You can, and in blocks of hours, but you cannot do that with solar, you cannot do that with wind. So, you must transition to operate at the speed and the latency that your asset operates at. So when you make this transition and you start relying on a streaming first composable architecture, you're going to stop leaving money on the table and you're going to future proof your business so that everything else that comes on top of it, you are going to be ready to react to it in milliseconds.
Yeah, 100%. That if you want, like you can probably run a like a nuclear power plant or a coal power plant with batch processes, but not a wind farm or a
Yeah.
solar panel, right? So it's really true.
All right. Thanks, Eric. I think we've reached the end of what we have time for today.
Mhm.
The questions. So I think it's time for us to say goodbye and to hope that our listeners today get in touch with us and that they explore what Hivemind and Ververica showed them today.
Thank you very much for having us, and have a great day.
This has been a pleasure. See you soon, Eric.
See you soon. Bye
Bye.
bye.